In section 15.5, we want to look at directional derivative and gradient. These are slightly tricky topics, so we're going to spend a few pages just developing the ideas and a sense of what they look like. So now remember, when you have some three-dimensional surface, z is equal to f of x, y, and it's with respect to x and y, if you cut into it with a plane that would be y is equal to a constant, then you have this tangent line right here, and the slope of that tangent line would be z sub x, right? The partial derivative of z with respect to x. Okay, but you could also cut into it with z sub y, right? Or with a x equals a constant. So right here, you can see you're cutting into it with a plane, x equals a constant right there. And that gives you this line right here. And the slope of that tangent line would be z sub y, or if you will, the partial derivative of z with respect to y. I got my letters messed up there. Partial derivative of z with respect to y. There, I don't know if I made it better. All right, so let's look at this together. So we have down here, we have this x equals a constant. See, this is the x-axis. So this plane cutting in right here is x equals a constant. And when we do that, when we do that, we have this line that is tangent at that point P. And the slope of that line is z sub y, right? The slope of that tangent line that points in that direction, right? And here's the point P right there. Okay, then there's the other one. So if you cut into it with an y equals a constant, right? So here's y equals constant. You can see it's got this kind of picture right here. That gets you this line right there. And that line has a slope that is z sub x. Okay, so we're seeing the rate of change in z as we move around the room. So if we're this point right here, so if point P is right here, its shadow is cast right down there. Now you can see that there's actually vectors in the xy plane that are kind of moving along. So we have, let me think, this vector here, right? That's parallel. I did double C's in there. I don't know why I did that. Vector C, vector. I did it again. One second. There. I called it V1. It says vector parallel to the x-axis. And there's another vector right here, which I'll call V2, which is a vector, there I spelled it right, parallel to the y-axis. Okay, so what are we seeing when we look at these slopes, right? When we walk in the direction of one thing, right, if I move this way, then that slope is telling me the rate of change in the ceiling. So if you imagine you're walking along this path, how is the ceiling above you changing as you move along that path? That's what the slope tells you. And same thing if you go this way, right? If you're moving along this vector, then the ceiling is going with you over that, and this slope changes, right? So these two slopes represent the rate of change in the ceiling as you walk in the direction of one of those vectors. There we go. I just wrote that up. All right. So if that's the case, then the question becomes, how do you determine the rate of change if you want to move in any direction? Not just parallel to the x-axis and parallel to the y-axis, but you want to go any which way you want, right? We need a way to do that. But first we want to visualize it. So if we look at this graph, so here's the surface three-dimensionally, and we have some arbitrary plane that has a direction vector down here, right? So it has this direction vector u, if you will, down there. And you're saying, hey, I want to go in the direction vector u. So let me put that in. Direction vector is u, like that. So I want to go like that. So you create a plane built on that vector, which is this big pink plane here, and it forms this curve right here. So you have this curve where the plane intersects the surface. So then at one of the points on that plane, you would have a tangent line like that. And the slope of the tangent line is equal to the directional derivative, that's the way we call it, directional derivative at the point PQ. So I put PQ kind of directly over, right? See, there's PQ down there. So I'm trying to go straight above it, right? At PQ in the direction of our U vector. Oh, that's a mouthful. So we need a quick way to notate that. And it's right here. So the directional derivative, we give it this notation, which is capital D U F. Right? Capital D for directional derivative. And the easiest way to think about this, and you can find videos of this. This actual video doesn't work anymore, so don't bother going to that because it doesn't work. But you can find them on YouTube. But the easiest way to think about this is just what I was just talking about. You imagine you're standing here, like this is the floor, and you're walking in that direction. And the directional derivative is the rate of change of the ceiling above your head, right? How fast is the ceiling going up or going down above you, right? That's the best and easiest way to think about the directional derivative when you want to imagine it in your own brain. I'll just highlight that right there. Okay, so we can kind of imagine it now. We can see it's how the ceiling's going to change over our head, but we need to figure out how to find it. All right, so let's start by finding the equation for the line r of t in that diagram. So r of t is the line that's in the 2 space. Here, if I go back right here, you can see r of t is this line that's on the xy plane right there, right? So that's the r of t. It's the equation of the line that's in the direction that you want. Okay. Well, that's back to the first unit of the class, right? How to find the equation of a line. So we need a direction vector, which we have, right? It'll be u. And usually we abbreviate u. We'll do u1 and u2, right? So it'll have a couple coordinates because it's on the xy plane. It technically doesn't have to be the xy plane. It can be any plane, but it's always easier for us. And then we need a point PQ, which we have, right? So we go from the origin to PQ, we make a vector out of it, and that's PQ in vector form. All right, then we put these together. R of t is equal to u1, u2, comma u2, times t plus pq. Or if you will, that's u1t plus p and u2t plus q. All right. So that means we can write parametric equations for x and y. We know that x must be equal to u1t plus p, and y must be u2t plus q. Sure. Now, over that line is some surface. So this is the equation of the line. This is parameterizing that line that's on the xy plane. But overhead, there's a ceiling, which is that surface, right? So this surface is our ceiling, where x and y satisfy the equations we wrote. So we want to make a chain rule tree diagram of that situation. So let's think. We have z. Z was broken out into x and y, x and y. But when I look at x, x is defined only with variable t, and y is defined only with variable t. So it's a pretty easy chain rule diagram, all things considered. So that means that dz dt is equal to the partial derivative of z with respect to x times the derivative of x with respect to t, plus the partial derivative of z with respect to y times dy Notationally, they're slightly different just because z has two options. When that's the case, we use the delta. X only had one option, so we use the d, but functionally they'll work pretty much the same. So this is f sub x, right, because our function z was f. So f sub x times dx dt. Well, dx dt was u1, right? So if this is the case, then dx dt, the derivative of that with respect to t, is u1. And the derivative of y with respect to t is u2. So this is u1 right here plus f sub y u2, which is the formula we have right here on the formula sheet. So a convenient way to do this and do this calculation is to write it as a dot product. So the directional derivative of f with in the direction of u is, if you take f sub x and f sub y and you dot product it with u1 and u2, you end up with the gradient of f times u1, u2. And that leads us to our last term of these pages, which is the gradient. The gradient is, it's called the del function, so the del of f. So it's f sub x, f sub y. So d uf, the directional derivative of f in the direction of u, is equal to the gradient of f dot product with the u vector. Where, of course, u is the unit vector. That's why we keep using u. Unit vector in the direction of your motion, the direction you're walking. So now we have a sense of what the directional derivative is, right? It's how the ceiling above your head is changing as you move in the direction of u, and this is how you're going to calculate it. But we're going to save calculating it for the next video because this took us a while.